black hole microstates versus the additivity conjectures. Take it away.
Okay. Awesome. So yeah, thanks very much for asking me to come talk. So yeah, this the paper that came out back in December was written with Patrick Hayden. And it's a bit of an odd paper because it sort of doesn't quite know what field it's about. Instead, we sort of either have something to say about quantum information, or we have something interesting to say about quantum gravity, but we sort of don't know which it is. So I guess we leave the question of which half of you guys should be interested in this talk and which half should not care at all for you guys to work out in future follow-up work or whatever. But yeah, so essentially we have these two possibilities, that either we have what we call extensive violations of the additivity conjectures. That's going to be a thing about quantum Shannon theory, or we're going to have a set of black hole microstates that we call disentangled microstates that can sort of explain the whole Bekenstein-Hawking entropy of a black hole in ADS CFT up to at most some order 1 correction. So at least one of these two things is true. Could be both. But we think either of them is a sort of relatively surprising, interesting result in the same field. So it's, yeah, we think the paper is interesting, even though we don't know which of these two things is actually the thing that happens. Okay, so really a lot of what I'm going to spend my time doing is just providing a bit of background on sort of what these two things are and what we're going to mean by them, because, you know, obviously they're pretty disparate fields. The set of people who are familiar with both topics may be relatively small. And then sort of in doing that, I will pretty much inevitably explain why one of them has to be true. And then, yeah, I'll talk a bit more about, you know, if possibility 2 is true, what does it mean about black holes, and how does it connect to a lot of things being talked about over the last decade or two, sort of firewalls, fuzzballs, all that sort of speculative stuff, and what it maybe hints about how that might work. Okay, so let's start with possibility 1. So first part of this talk is just going to be some very basic quantum information theory, quantum Shannon theory. And really I'm going to start with essentially the very first question anyone asked that could meaningfully be called quantum information theory. And this was actually a question asked by Claude Shannon himself, which is the following. Let's say we have some quantum channel, mathcal n, and let's say we want to use that quantum channel. That quantum channel is a way for Alice to communicate to Bob. And Alice is able to use that channel lots of times, and she wants to send as much classical information as possible. Okay, so the question is, in the limit where you can use the channel little n times as little n goes to infinity, what's the rate at which you can send classical bits? Okay, so here on the left, we have Alice. It's a very boringly gender conforming Alice, but she does have a very long neck that's about half the length of her body. So that's the least interesting about her. And, you know, she's wanting to send this message to Bob, message I. She's just somewhere between 0 and 2 to the r times n. Okay, so she's wanting to send r times little n classical messages to Bob. How does she do that? Well, all she can do is you know, input some density matrix, rho I, to all these n uses of the channel, where that input density matrix obviously depends on I, right? She sends a different code word state depending on which message she wants to get to Bob. And then Bob is going to receive rho I, but he's going to receive a sort of noisy version of rho I. It's going to have n copies of the channel mathcal n applied to it. And then Bob wants to use that information to work out what I was, okay, work out the message that Alice sent. So it's a very basic fundamental question you'd want to ask. And And to a large degree, it has obviously been answered. We made a lot of progress in quantum channel theory in the last 20 years, 30 years. So the first thing you can pretty easily show is that R times N has to be less, so the number of classical bits successfully sent has to be less than the mutual information between this state, n tends to n, little n, or acting on rho I, that Bob receives, and the original message I. Okay, the amount of correlation between those things, upper bounded by the mutual information between them. And so that upper bounds the amount of information that can successfully be sent. So this is called the Halevo bound. And in fact, there's sort of a converse statement as well, which is that if we have any set of code words rho I, any set of states rho I, then we can find a code that in the limit where the number of channel uses goes to infinity, roughly achieves the rate. So if these code words involve m inputs, then it can roughly achieve the rate 1 over m times this mutual information between the state Bob receives and x. Okay, so if each code word rho I is using m uses of the channel, then the rate it achieves obviously 1 over m times the mutual information, because you've used up m uses of the channel in each block. Okay, so this gives us this theorem that at a certain level completely answers the question of the question above of like how much classical information can we send. It's just first you want to sort of optimize over your choices of rho I's to use, right, in order to make this mutual information as big as possible. And then the second thing you want to optimize over is the sort of number of channel uses that you use in your definition of each state rho I. Okay, so you just maximize, take the supremum over m of 1 over m, this thing. And that supremum over the rho I's gives, for the channel m, right, that gives something called the Halevo information here. So the full formula for the classical capacity is what's called the regularized Halevo information. So it's this mutual information optimized over all input states rho I, and then optimized over taking as many channel uses as you need. Okay, so at one level, that's the answer to the question. We're done. It's just given by this formula, this regularized Halevo information, but there's a problem. And that problem is that this quantity can never be sort of numerically or anything actually computed, right? It involves arbitrarily many uses of this channel. We have no idea how big m needs to be to sort of get close to this sort of supremum over m. Maybe you try 1 billion uses of the channel, numerically search with some ridiculous supercomputer or quantum computer or something, and you find that the maximum rate is like 1 qubit, but then it turns out by using 1,000,001 uses of the channel, you could actually send 1,000,000 qubits per use, just because there's some much better state. We sort of have no way to know that isn't the case just from this formula here. Okay, so that's obviously a problem. We've like answered the question, but answered it in a useless way. It's not actually, it's sort of like circularly answering the question and saying, well, by definition, it's this thing. So yeah, it's like answering it by saying, oh, the classical capacity is just equal to the maximum capacity that you can send through it. You haven't usefully answered the question. But for classical capacities, for the classical channels, I should say, if n is a channel that only sends classical information through it, no quantum information, then it turns out the sort of story is much, much, much simpler. And the reason that it's much...
Can I ask a stupid question here?
Yep.
This x, it's like a number, right?
So this should be a chi. Halevo chi.
Okay.
It's a very bad chi. Yes, it's a number that is defined.
Yeah, go ahead.
Yeah, so by definition, chi of some channel n is defined as the supremum over a set of row i's of I for n acting on row I, tensor x just being in the state I.
I see. So there were x's.
That answers your question.
So there's some chi's and there's some x's. So the x's are states and the chi's are.
Yeah, the x is the classical subsystem just storing the message I. Chi is just a quantity that it's a number that counts how much information can go through. Okay.
Wait, sorry. So x is a quantum state, or it's a classical?
X is a classical state. X is the classical message. So x is literally just the label I. B is the quantum system. B is the quantum state that Bob receives, the output of these quantum channels.
Okay.
Okay.
So I'm used to, but the mutual information normally have two quantums. So this is like a special case or something.
Yeah, it's just a quantum classical mutual information. So you can think of this as a quantum state. It's just that it happens to be the case that the system X is always classical, right? There's no off diagonal elements.
Okay.
But you calculate it with exactly the same formula.
Okay. Thank you.
Okay. Great. So if the channel Xn was classical, then we then have a completely classical mutual information. That's just the classical formula for the classical capacity of a classical channel with no quantumness showing up. But in that case, it turns out we don't need to do this supremum over the number of channel uses times 1 over m times chi, because that whole complicated formula that you can never compute, it's just equal to what's called the single letter version of it, which just means you have a single use of the channel n, and you look at the supremum over row i's, which in that case would just be classical probability distributions, but you don't need to take a supremum over the number of channel uses. Okay, and so the reason that you don't need to take that supremum, or it sort of doesn't help to do so, is that for a classical channel, then this Halevo information is what's called additive. So if we have the sort of Halevo information for the tensor product of two channels, then it's just equal to the sum of chi of n plus chi of m. Okay, so in turn that means that the Halevo information for the tensor product of m copies of n is just m times the Halevo information for one copy of n. Okay, so if this was true for quantum channels as well, it would be incredibly nice. We'd actually have a useful answer that we could compute. And more than that, it would be telling us something about the sort of optimal way to send quantum information, classical information to a quantum channel, which is that it doesn't help to use code words row I that sort of entangle between different inputs to the channel, right? If I'm using this channel lots and lots of times, as long as I'm only sending classical information through it, then I might as well just send sort of uncorrelated quantum states through it. It doesn't help me to sort of use row i's that are maybe like a bell pair between two different uses of the channel. Okay, so that wouldn't help if this thing was additive. Whereas if it's not, it just means we have no idea what the best codes are, and all you can do is do a brute force search of everything you could possibly try, even if it's like infinitely long. And we haven't provided any useful new information beyond try every possible code and see what works. So it would obviously be very, very, very nice if this was true, that this Halevo information was additive, and it was what was called the additivity conjecture. Back in the sort of noughties or so, then this was a big question in quantum information. But then in about 2009, I think, Matt Hastings answered the question, and the answer is a resounding no. So this is just not true. The additivity conjecture is false. Hastings found a counterexample by constructing random channels and showing that most random channels for a certain type of random channel must violate this thing. But the channels he found didn't violate it very much. In fact, they didn't violate it very much at all. The largest known violations, even, this was a big subfield for a while after Matt Hastings wrote this paper, people searching for new violations of additivity and so on. People tried really quite a lot. And whatever they did, whatever weird, wacky, random channel constructions they came up with, the violations never got larger than about 1 bit. In fact, it's almost exactly 1 bit is sort of the biggest violations that are known. And this is true no matter how big your quantum channel is. Your quantum channel could have an input that consists of 1 million qubits, it have classical capacity of 100,000. And it's still the case that we don't know of any examples where sort of using this naive single letter formula will give you the wrong answer by more than about 1 bit or so. So this is sort of maximally unsatisfactory, right? The sort of simple story that just, it's all easy and you only need to think about one channel use is wrong. Multiple channel uses can help, but they don't help in any significant way. It's just you get a tiny marginal benefit sometimes in some random constructions. We don't really know why. It doesn't there's no crazy huge advantages to using entangled code words instead. It's just a weird no man's land of no one satisfied about anything. Okay, so that's sort of the situation of this conjecture right now. But one thing I should say is that in Matt Hastings' paper, he doesn't actually calculate any classical capacities explicitly at all. And that's because he's not actually directly showing that the Levo information isn't additive. Instead, he's showing that something else isn't additive, which is what's called the minimum output entropy. And because this is the thing that I'm going to be arguing maybe isn't additive, I should briefly define what this is. So the minimum output entropy of a channel is just defined as the minimum over all states rho of the von Neumann entropy of the output state n of rho. Okay, so for the identity channel, for example, this would just be 0 because I can put in a pure state and then the output will be pure and we'll have entropy 0. But for some noisy channel, maybe no matter what state I put in, it has some non-zero amount of entropy at the output. Okay, it's a non-zero minimum output entropy. And then we can compare the sort of minimum output entropy for 2 copies of the channel, minimizing over all input states potentially entangled between the two to both inputs of the channel. And we can see whether that is smaller than sort of twice the minimum output entropy of 1 copy of the channel, right? Clearly, it's at least as small as it because I can just input a product state, but maybe using entangled states, I can make it even smaller. So before Matt Hastings' work, Peter Shaw had already shown that this quantity, this minimum output entropy, won't be additive, even only if the Halevo information won't be additive. Okay, so the Halevo information is sort of the one we're really interested in because classical capacities are a big deal. They're this fundamental thing that you care about in quantum information. But this minimum output entropy additivity feels like sort of something easier to work with, easier to prove. And indeed, this is the thing that Matt Hastings actually proved violated, had additivity violated. And the size of the violations for this minimum output entropy are the same as the size of the violations for the classical capacity.
And the inequalities are in the same direction in both?
So no, it's the opposite direction actually. So in this case, sort of one direction is trivial for each of them, right? So in this case, with chi, we're maximizing over all rho I, right? So if we have the tensor product of 2 channels, then clearly it's at least as big as the sum because we can put in product rho i's. but maybe by using entangled row i's, we can make it even bigger. In the other case with the minimum output entropy, we're minimizing over row, right? So it's by using some entangled state row, then maybe we can make the output entropy even smaller. Yeah. Okay, so we're now sort of ready to restate possibility one a bit more precisely. So what it's going to be is that rather than having just sort of these order 1 qubit violations, then actually arbitrarily large violations of additivity and minimum output entropy exist. And in fact, these violations are what we call extensive, which just means they grow linearly with there's a family of channels with a number of qubits that grows as little n, and the size of the violation grows linearly with the number of qubits in the channel. Okay, that's what we call an extensive violation. So if this is true, what would it mean? It would mean that this like simple formula for the classical capacity, where we sort of don't optimize over arbitrary numbers of channel uses, like the only formula that we can actually directly compute, is not even approximately correct. It's not like it just gives you the right answer up to a bit or so. It can just be arbitrarily wrong. Okay, so that's possibility one. Obviously would be fairly significant within quantum Shannon theory. Now I'm going to turn to something completely different. Now for something completely different, which is going to be possibility two, which is this thing about black holes. Which at a surface level seems very, very different, but we'll sort of see reasonably quickly how they're going to be pretty similar. Okay, but to start to introduce possibility two, the first thing I'm going to need is this thing called the Reactangi Formula, which to many of you may be very, very familiar. Some people from more quantum information background maybe haven't heard of it. But what does it say? Well, we have this thing called ADS-CFT, this duality. And this duality relates a quantum field theory on the boundary of your space-time to a theory of quantum gravity in the bulk. Okay? And the Reactangi formula is an element of the so-called dictionary that relates these two sides. And what it says is that if we have some subregion of the boundary that I call big B here, and we try to compute the entanglement entropy of sort of reduced states on that boundary subregion, then that answer can be calculated using the bulk physics, using the gravitational physics, and it's just given by the area of the smallest area surface, so this green surface here, that's sort of anchored on this boundary region, that's homologous to this boundary region. And in fact, it's that area divided by 4 times Newton constant. Sort of looks like Bekenstein-Hawking entropy. Okay, so let's look at an example of this. You could imagine some space-time that has a sort of black hole sitting in the middle here. So this should be a black hole. Let's look at the horizon of the black hole. And we can look at what we can look at some boundary subregion B, which I'm going to take to be slightly less than half the boundary. What's the smallest area surface that's homologous to B? Well, this boundary is sort of infinitely far away, so it doesn't want to stay out near the boundary. It wants to go into the bulk, but it also doesn't want to hit the black hole. So it sort of goes around the side of that black hole and looks something like that green drawing there. Okay, so it just has some area, which is equal, I'm going to call A naught. Okay, so this formula would be true. So this formula that the entanglement entropy of B is given by this area A naught divided by 4 times Newton's constant, be true for sort of many different states. In particular, it's true for sort of a thermal black hole state, but it's also true for some pure black hole state, at least as long as it's a so-called typical black hole microstate. The same formula will apply. Okay. But we can also consider calculating something different. So let's now consider what's called a two-sided black hole. So in the boundary field theory, this is just what's called a thermofield double state. It's psi equal to sum over different energy levels, En of the boundary CFT, e to the minus beta En over 2 times the energy eigenstate En on each side. Okay, so this is just a purification of the sort of Gibbs ensemble, the thermal ensemble. And this is dual in the bulk to what's called a two-sided black hole, which means a black hole with this Einstein-Rosen bridge connecting it to a different boundary. So we have a left boundary and we have a right boundary, and they're connected together by this Einstein-Rosen bridge or wormhole. But otherwise, the geometry looks the same as this geometry of the black hole we had up here. Okay, so now we're going to consider not just the entanglement entropy of a sort of region B on one side of the black hole. That would just be the same as before. But instead, we're going to consider the entanglement entropy of a copy of the region B on the left boundary plus a copy of the region B on the right boundary. Okay, so I've sort of drawn a very bad cartoon of this Einstein-Rosen bridge at the top here. But we can also just think of it as two copies of this black hole with the horizons glued together. And it turns out, you might think, okay, the minimal area surface homologous to this thing just looks like two copies of the same surface we had before, one on either side of the black hole. But it's not. The actual answer, at least for a big enough black hole, is that it sort of is a surface that tunnels through the horizon. It goes through the wormhole, sort of starting out at one boundary over here and ending up at one boundary here. So you can really think of it instead as two copies of a surface that starts out at the boundary of B and then just goes down to the horizon and it's glued onto the other side. Okay? And the reason it's this rather than just two copies of the original surface we had before is that the sort of area of this surface that gets attached to the horizon is, which I'm going to call A1, is smaller than the area A0 that we had before, okay? Because it doesn't have to go around the side of the black hole. It's like it just gets glued onto the black hole horizon and skips having stuff around the side. Okay. So hopefully sort of starting to see how we might get to something involving violations of additivity and minimum output entropy, right? We have some entropies. Here we have two copies of the channel. Before we had one, and there's a difference between them.
Is there any estimate of how big is this difference between A0 and A1?
Yeah, it depends on the size of the black hole, number of dimensions, and so on. But the difference between A1 and A0 isn't really important because if you had an entropy, when you go from areas to entropies, you have this multiplying by 1/4g, right? And in appropriate limit, where the bulk physics becomes classical, then g becomes very, very small. So no matter what difference we have between A1 and A0, then the difference between A1/4g and A0/4g becomes very, very large, and in particular, it scales linearly with the sort of size of the boundary CFT. The number of qubits in the boundary CFT is proportional to 1/g. But this difference is something you can compute. In low dimensions, you can compute it explicitly. In high dimensions, numerically at least. But it just depends on the temperature of the black hole and stuff. It's not the interesting thing to worry about.
So this difference has nothing to do with the huge violation of the conjecture or the small. Yeah,
the huge violation comes because we have this 1/4g, and then we tune things so that g becomes really, really small. Does that make sense? So yeah, like these areas, they have some units, right? So yeah, we got to divide by 4g to get something unitless, and that's what makes it really, really big. Okay. So how are we actually going to get a violation of additivity? Well, let's just for the moment make some very strong assumptions about the existence of a certain code space of CFT states. Okay. Let's suppose that we can construct a code space that heuristically, sort of subspace of states that heuristically contains all black hole microstates, but nothing else at all. Okay, in particular, let's assume firstly that any sort of pure state in H code is just a typical black hole microstate. It looks exactly the same as a typical black hole microstate, i.e., if we look at the entropy of some region B, it's just given by A0 over 4G. Okay? So certainly code subspaces like this exist. If you take sort of two random typical microstates and then the code subspace formed by their span, then every state in that Hilbert space will have satisfy this entropy property. But we're wanting a code subspace that contains sort of all black hole microstates. So that's something much stronger. And so the second thing that lets you get, if you really have all black hole microstates in there, is that by using two copies of this code subspace, then you'd actually be able to find an approximation of this thermofield double state. So by entangling these two code subspaces, we'd be able to make a two-sided black hole, like this thing up here. Okay? Okay. So if those two assumptions were satisfied, then we'd be able to find an extensive violation of additivity of minimum output entropy. How do we do that? Well, we're just going to define the channel N to be a channel that takes as input a state in H code, okay, and then the output will just be the reduced CFT state on that boundary region, big B. Okay? By this first assumption here, then for any state, any input state to one copy of the channel, then the output entropy, which is just the entanglement entropy of big B, is going to be A0 over 4G. On the other hand, by assumption 2, if we have two copies of the channel, we have two copies of the code space, we can input arbitrary states to two copies of the code space. We can input this entangled state that gives the approximation of the thermofield double. Then what will the output state be? Well, it will be the output state on two copies of big B, so this B left and this B right. What's the entropy of that thermofield double state? Field double state on B left tends to be right. It's just 2 times this A1 over 4G. Okay? So the minimum output entropy is clearly less than or equal to that. So it's less than or equal to 2A1 over 4G. And 2A1 over 4G is obviously strictly less than 2A0 over 4G. Okay. So this would be 2 times the min over rho of S, N over rho. Okay, so we now have a violation of additivity. The minimum output entropy of 2 copies of the channel is strictly less than the minimum output entropy of 1 copy of the channel. More than that, as I said, it's actually a very big violation, because all we do is we take the limit where G becomes very small, where the bulk becomes classical. It's like the large N limit of the CFT. So the sort of number of qubits describing the CFT is order 1 over G. This violation actually grows extensively with the size of the input channel as we take the limit where we take a sequence of CFTs that has weaker and weaker coupled gravity jewels. Okay, so that would give us this extensive violation. We would have proved that property 1 is true, at least at a quantum gravity level of rigor. You might worry about things like regularizing the CFT and stuff, but it's pretty clear that those shouldn't be problems. What should be a problem is whether there actually exists this code subspace H code that has these 2 properties. Okay. So let's think about how one might actually go about building this code subspace. Like, finding an H code that has these properties. Okay, so sort of first guess to get a subspace that contains all black hole microstates is just include in your code subspace every state with approximately the right energy. Okay, this thermofield double state Obviously, if we go back to this formula up here, technically it involves the superposition over sort of every energy eigenstate, but by usual way things work semi-classically, this gets dominated by energies near some saddle point value. If you include a sort of range of energies about that saddle point value, as long as you include a large enough energy window, you can easily approximate the thermofield double state using 2 copies of this code subspace. You'll have some small error in your construction, but that can't change the entropy very much. So we'd still be able to find a additivity violation. Okay, so it seems like we've got assumption 2 nailed down, but it's also pretty clear that this code subspace will not obey assumption 1. Okay, so assumption 1, remember, was that every state in this code subspace looks like a typical black hole microstate. But if we just have all states in some wide energy window, that's going to include all sorts of non-black hole states. It will include states, for example, that just have sort of look like perturbations about vacuum ADS with a load of radiation really far out near the boundary. That can account for the energy. That's going to be a state that's in this window. And so it will be in this code subspace at this point. And it will have a very different entropy that can be smaller than A1 maybe, depending on exactly what the state is. But it's certainly true that we shouldn't expect this H code to obey assumption 1 yet. But what should be true, the sort of folklore, is that this code subspace should be dominated by black hole microstates. Sure, there's some states in there that are like weird and crazy and have all sorts of other stuff going on, but they're like out of equilibrium states. The stuff that wants to happen is everything becomes a black hole. So sort of if I pick a random state in this subspace, then with overwhelming probability, it should be a black hole microstate, a typical black hole microstate. Seems like maybe we can fix this problem just by like getting rid of a few badly behaved states. So let's imagine doing that. Right, what you do is you just try to iteratively improve this H code, make this assumption 1 hold by searching for states in it that have a very small entanglement entropy, a very small S big B, and just throwing them away and just restricting to the orthogonal complement of those states. Okay, so we just take a few, search for them, throw away the sort of smallest entropy state, then throw away the smallest entropy state orthogonal to that, then the smallest entropy state orthogonal to that. Just keep doing that and making our H code smaller and smaller and smaller. And the good news is that we can do this for really a very, very long time and still be able to make a good approximation of the thermofield double state. Okay, the thermofield double state is a very highly entangled state that does not have much support on any given microstate on either side. So it turns out we can throw away order the Bekenstein-Hawking and order each of the Bekenstein-Hawking entropy different orthogonal states and still have a code subspace that approximately looks like the thermofield double state. As long as we don't throw away order e to the S states, say we throw away e to the 1 minus delta times S, right? That still seems a huge number of states, but we'll still be able to make the thermofield double state up to some tiny exponentially small error of sort of order e to the minus delta S. Okay.
Sorry,
so we're just going to
quick question. So
Yep.
you're thinking of states in the double theory or in the single theory?
No. I'm thinking of states in the single theory. So we're taking this code subspace. We're looking for states in that code subspace that have a small output entropy, and we're throwing them away out of the code subspace. And then we're trying to ask, can we still reconstruct the thermofield double using 2 copies of that code subspace? And the answer is, as long as we don't throw away too many from the sort of single-sided code subspace, we can still entangle 2 copies of the code subspace and make a good approximation of the thermofield double.
Yeah, my confusion was the definition of this quantity S of B. So this is not like the entanglement entropy of the state?
No, this is the
output?
This is the entanglement entropy of the output, and the output is the reduced state on like slightly less than half of the boundary.
I see. Okay.
Right, so we just have one black hole here, but we have an entanglement entropy between the sort of left side of the boundary and right. I shouldn't say left and right because that sounds like a two-sided thing. Between this boundary region here and the complement. Okay.
I see. Thanks.
Okay.
Question.
Okay.
So if you need a linear subspace, right? This code subspace needs to be linear.
Yes, exactly.
Is there
So
a guarantee that even if you throw away like a basis state,
no,
you keep a bunch of basis states that look like a black hole, that there isn't like a weird linear combination that does not look like a black hole?
Yeah, so we're throwing away the ones that don't look like the black hole. Okay, so we'd have exponentially many. Yeah, so there's no guarantee you end up with everything looking like the black hole at any point. Let me give a simple example of how this wouldn't work. Let's say your channel was just a partial trace over some subsystem. Okay. You just looked, your input was just like the entire Hilbert space. Then you could say, okay, let's throw away states that have a small output entropy. Well, what would they be? They'd be product states, right? And so you throw away the product state 0 tends to 0. And then you'd restrict to the orthogonal complement of 0 tends to 0. And then you'd find another state that has 0 output entropy, which might be 0 tends to 1, right? You throw away that, you look at the orthogonal complement of that. You're going to end up throwing away, you're going to end up just throwing away states until you have no states left at all, and always have states in there that have 0 entanglement entropy, right? And you'll just end up with a basis of states that is a product basis. Okay, so you'd have just found a set of states, all of which have 0 output entropy. And that's okay. So that's one possibility for what happens in the black hole case too. And that's basically going to be our possibility too. Okay, so there's two things that can happen. One is we throw away any states that have small enough output entropy, sort of entropy close to A1 over 4G. And we do that for a while. And at some point before we've thrown away exponentially many of them, we just run out of states to throw away. And now we have a code subspace that still contains sort of almost all black hole microstates, and which has this property 1 up here, right? Every pure state in it, or maybe it doesn't have entropy as big as A0, but it has entropy significantly bigger than A1 over 4G. And then we'd have found this additivity violation.
And can I ask a question also?
Yep.
I mean, if I look at the state that Hawking calculated, if I look at that state, which is an entangled state representing the vacuum near the horizon, then it's entangling states that don't look like the vacuum at all. I mean, there's particles on the left and the right. It's very singular things that almost look like firewalls. Yes,
exactly. So yeah, it's exactly right. That you know these disentangled. I'm going to comment in a bit about what these disentangled microstates seem to have to do with firewalls.
Okay,
but you're thinking exactly along the right lines.
Okay.
Yeah. So the other possibility is that we just keep finding them and keep finding them and keep finding them, and we do find order each of the Bekenstein-Hawking entropy different states. Okay. So then we would have found each of the S orthonormal states that every single one of them have a sort of entropy of this region big B that's roughly less than or equal or very close to up to an order 1 correction, maybe to A1 over 4G. Okay, so this is what we call possibility 2. Have this orthonormal set of what we call disentangled microstates. So these are very atypical. If we just look at like a random state, you know, it would have much more entanglement. But we have this orthonormal set of them that can account for the entire Bekenstein-Hawking entropy, up to a most some tiny little subleading order 1 correction. Okay, so this would be like, you know, this would be roughly analogous to the set of product states you might find, right? It's a basis of states, but each state in the basis is very atypical in terms of its entanglement properties. So there's no reason this can't happen. Entanglement is a nonlinear quantity. You know, you can have a basis of states where every state is atypical. so sort of why should you care about this? What's interesting about it? Well, the answer is that it sort of really quite strongly suggests that these disentangled microstates should have some sort of structure, something happening at or outside their event horizon. And if these disentangled microstates are accounting for the entire Bekenstein-Hawking entropy, then sort of you have a linear set of states with structure at the horizon that can basically explain the whole Bekenstein-Hawking entropy. Okay, that's obviously
exactly what the possible proposal has been saying for 10 years.
Sure.
Why do you want the horizon, by the way? Why do you want the horizon, though?
I say at or outside the horizon, so maybe there isn't a horizon. That's completely consistent with this. What I am saying is that it can't look like a black hole all the way to a horizon and then have a smooth horizon and smooth geometry behind that horizon. Okay. The other thing I would say is that this doesn't necessarily suggest something as strong as sort of the fuzzball proposal or the firewall proposal, though it's certainly consistent with that, because the fuzzball proposal or firewall proposal would normally say that a sort of typical black hole microstate has structure at the horizon, right? Whereas these disentangled microstates are very atypical. It's just that there's a linear set of them that sort of span the Hilbert space of microstates.
But that's exactly
right.
what I think. But that's exactly what fuzzballs are saying. So fuzzballs are saying that there's a the Hilbert space is spanned by some smooth geometries. The typical state in the Hilbert space will be some crazy overlap superposition of these smooth geometries, which doesn't make any sense from classical physics. But you can find a large enough set of states of classical microstate geometries which can actually span the Hilbert space.
Would you say that a typical state has a horizon then?
No, I would say, I mean, at least in the undefined system, which, we're constructing this explicitly, we have many states and they don't have a horizon. And they have exactly the same features as typical states. So I would have a very hard time if a typical state had a horizon and my state didn't have a horizon. I would have a very hard time understanding why.
I mean, if you allow the question of whether there's a horizon or not, or whether there's a smooth horizon to be nonlinear, then having a basis of states that do not have a horizon does not imply that every state doesn't have a horizon. Now, there's all sorts of reasons that you could object very strongly to having the question of whether there's a smooth horizon or not be nonlinear. But I'll comment on that.
Complementarity picture. Personally, I don't like it.
Sure.
Matur likes it a lot, but personally, I don't like it at all. So
Sure.
That's my.
Yep. Okay. So why do these disentangled microstates suggest that you should have some sort of structure at the horizon for them? Well, let's assume that the microstate, you have some microstate that firstly is going to obey the Reactangi formula, or really sort of the QES prescription, but I'm not going to worry too much about quantum corrections. You can deal with them. Secondly, want it to look like sort of an ADS Schwarzschild black hole as far as the horizon. Okay. And thirdly, want the horizon to have a sort of smooth geometry. Okay, but other than that, I'm going to allow, maybe this thing has a totally crazy interior with all sorts of wacky stuff going on in the interior, but that's all like behind the horizon. As far outside and sort of at the horizon, it's just ADS Schwarzschild and then a smooth horizon. Okay, I claim that such a microstate cannot be disentangled. The entanglement entropy of this region big B needs to be strictly bigger than A1 over 4G. Okay, so why is that? Okay, let me just give a heuristic argument. You can be more precise about this.
What do you mean by not disentangled? I'm trying to understand. I don't.
But my definition of disentangled is, I'm assuming we're in ADS CFT here. My definition of disentangled means that the entropy of this boundary region big B is less than or equal to A1 over 4G. Okay, it's just an upper bound on the amount of entanglement entropy between the two different boundary regions. Okay. So let's assume these three things are true. Then the entanglement entropy of this region big B can be computed by RT or QES, and it's going to have some RT surface. So maybe we have crazy wacky stuff going on in the interior. Maybe the RT surface goes into the interior and does some crazy wacky stuff in there. That's fine. We're not going to worry about what it does in the interior. Instead, we're just going to forget about that interior part and just look at the sort of part that's in the exterior geometry. Okay, what you can show is that the sort of just the exterior part alone is a surface that's homologous to the boundary region B plus part of the horizon, and the smallest such surface is the surface with area A1. Okay, so just the exterior part alone already uses up all the sort of allowed area. If you have any sort of smooth geometry in the interior, no matter what it does, then that's going to take you above area A1. You're gonna violate this bound. It's not going to qualify as a disentangled microstate. Okay, so really you need to use the time-dependent version of RT, HRT, and include quantum corrections, so QES and so on. But you can use max-min arguments to give essentially the same argument for those cases. Okay. So yeah, so yeah, if you have a smooth horizon, then we can't have a disentangled microstate. On the other hand, if you do have structure of the horizon, it's pretty easy to get something that has the right entanglement entropy. So sort of the easiest example I know of is just the so-called Hartmann-Maldacena construction, what's called a Z2 quotient of a two-sided black hole. Okay, so we just take our maximally extended ADS Schwarzschild, quotient it by the sort of left-right Z2 symmetry, and we get a space-time that has this sort of end-of-the-world brane that sits at the bifurcation surface here. Ooh, I did not mean to be in that. Sits at the bifurcation surface. So then what entanglement entropy do you get by the RT formula? Well, the answer is that the sort of RT surface is allowed to end on that brane. And so what it does is it's just forms the smallest surface that connects the boundary to the brane. That's exactly the surface with area A1. Okay, so if we had state with this Z2 quotient, which, you know, is pretty easy to construct in string theory, then yeah, it would have the right entropy. However, notice that this state still has a smooth, it doesn't have a smooth bifurcation surface, but it does have a smooth past and future event horizon. Okay, and that's completely consistent with this sort of quantum information point of view of what's going on, because if we have a disentangled state like this, and then we evolve it in time for a little bit, it's going to thermalize. So the entanglement entropy of big B is going to increase, and it's going to quickly become sort of a typical microstate from that point of view. Okay, so yeah, even though that's the only comment I will make, that normally in sort of fuzzball firewall proposals, other than sort of fuzzball complementarity ideas and so on, then we'd say that sort of every state has structure of the horizon. Here, the state just has structure of the bifurcation surface. It doesn't have structure at the event horizon. It still has an event horizon. But, you know, you can obviously also construct like fuzzball geometries, or, well, yeah. So to get these potential additivity violations, you need the black hole to actually be like a Schwarzschild black hole, not like near extremal or something. So we don't really have any like actual fuzzball geometries for that. But it's entirely possible that hypothetical fuzzball geometries for an ADS Schwarzschild black hole would also have the same sort of entropy. It's not obvious to me that
actually there are some non-extremal fuzzballs in ADS in flat space, not in ADS. I don't know if that.
But even like far from extremal?
Yes.
Really?
It's called the
Okay.
J-Mart solution. It involves essentially Euclidean Schwarzschild with some fluxes. There's a recent paper by Ibu, Ibrahim Abba, and Pierre Heinemann about them. So there
cool.
are some
If you could send me the link to that, I'd be interested.
Sure.
But certainly, I think we can't account for.
But I don't think you can put those in ADS. I think there's a problem with putting those. So they're
Okay.
in full 4D flat space, but I think they have a hard time being fit into ADS. So maybe that's one.
Yeah, I mean, I'm not going to try and make any definitive comments on the existence of these states, or states with structure of the horizon, because that's something that a lot of people have worked on for a long time, and I'm not really expert on, and I certainly bow to other people's superior knowledge on it. I just think the quantum information reasons to expect these disentangled microstates to exist is evidence that we should be, it's evidence in favor of that point of view. Final comment I'll make, sort of other reasons to think that maybe these disentangled microstates really do exist, is just thinking about what happens in tensor networks. So the sort of conventional way we model a black hole microstate in tensor networks is as some big sort of half random tensor sitting in the middle of some tensor network. And so then we can look at the entanglement entropy of some sort of region B of boundary legs. And for a typical black hole microstate, you'll just have some sort of half random tensor sitting in the middle here. And so the minimal cut will sort of go around the side of it like this green line. But we could form sort of a basis for the all possible tensors in the middle there by considering like product tensors, right? Where we have a tensor on the left things and tensor on the right things. And then we can just have a cut that sort of sneaks through the middle there without paying any cost because it's not cutting any legs. Okay, so this would be like the disentangled microstates. The sort of area of this cut is just the A1 of like getting as far as the horizon on one side and getting as far as the horizon on the other side. Of course, tensor networks are a very crude toy model. They have no sub-ADS locality. This sort of toy, in particular, this toy model of tensor network microstates, an actual ADS CFT, we wouldn't really expect them to, if you try to like make a tensor network description of ADS CFT states, it's not clear that you can do so and have the right energy to actually be a sort of black hole microstate with the same energy. But it's still suggestive of the intuition that these sort of disentangled microstates should exist. So yeah, that's basically all I have. I guess the sort of natural thing to end on is sort of, okay, so which of these is right? Is possibility 1 true? Is possibility 2 true? Maybe both are true, who knows? It's obviously an open question. We're not trying to answer it, just pointing out that it's there. Certainly, as a general rule, we know a lot less about quantum gravity than we do about quantum information. And people looked for large violations of additivity pretty hard for a long time, and they weren't able to find them. So I think, to me, possibility 2 being true would be like an order 1 surprisal thing. Like it's not obvious to me that it is true, but it's certainly not super surprising if it is. Possibility 1 would be more like, several bits of surprise. I think that would be like really, really quite unlikely, but if it's true, it's obviously a very big deal. So yeah, if I had to bet on one, I'd bet on possibility 2, but certainly it seems like it's both worth, encourage anyone who wants to both try constructing toy models of gravity, maybe that we could find additivity violations in. The most obvious toy model is tensor networks, and obviously those don't have additivity violations. The crudest toy models anyway. Or for trying to look for what these disentangled microstates could be. Some level, this is something a lot of people have already been doing with sort of fuzzballs and firewalls and so on. One thing that is different about these things, as I say, is that, my understanding of the fuzzball program is that people are generally looking for static geometries. Whereas these things can be explained perfectly easily by like time-dependent geometries where it initially has some crazy structure at the horizon, but then it just falls into the interior, falls to the singularity, and you get something smooth. So yeah, maybe things like that might be easier to find or construct. But yeah, I think it's very much open questions, but I think it hopefully inspires someone to think about something. Yeah, that's all I have. Thanks a lot, everyone.
All right, let's all unmute and thank Geoff. Now, we can record the questions, or we can stop recording and then start the questions. I'll leave it up to Ignacio to decide. I guess I can.
Question.
Go ahead.
Yeah. So Geoff, let me forget about space-time for a minute.
Yep.
And just talk about large N quantum field theory.
Yep.
Doesn't your tensor network example show that in large N quantum field theory, sort of generically, it's possibility 1? I'm sorry, I forget which was which.
Possibility 2 is the.
Possibility 2. Yeah.
I think it's some evidence for that. Like these disentangled microstates. I'm really quite confident that these disentangled microstates, like you can't just take a tensor network like that and then actually get a state with the right energy. It will have support in a big range of energies and
but
like
the energy was a question that had to do with the picture of this state as a black hole.
No, because when we're trying to construct the thermofield double state, we only need states. When we construct this H code and throw away states that have small entanglement entropy, then we start with an H code that only contains states in some energy window.
I see.
So certainly, if your starting code subspace was sort of the entire CFT Hilbert space, clearly you don't have product states because of UV divergences, but you have arbitrarily disentangled states. Like clearly you can find like arbitrarily many of them. That's not a problem. But if you're starting, from the sort of CFT question is if you start with states just within this really pretty narrow energy window, can you find within that energy window this e to the s different disentangled states?
I see. Okay. Thank you.
Yeah.
So I had a question.
Yeah, please go ahead.
It might not be directly related to the talk. I'm sorry, I apologize beforehand. I'm just worried that why couldn't the CFT tell us something about the interior of black hole?
Sorry, say that again.
I'm just worried as to why CFT couldn't tell us something about the interior of black hole.
I mean, I think the hope would be that it could. So the question was, why couldn't the CFTs tell us something about the interior of the black hole? I think it could, but we don't have enough understanding of the ADS CFT dictionary and like the CFT states maybe to in principle it's obviously you hope to, by studying the CFT, then you can learn all sorts of things about ADS, including the interiors of black holes potentially. I'm not sure I understood your question as intended, but maybe.
Yeah. So assuming the interior of black hole can be described by a semi-classical geometry like that of the exterior, why couldn't we use the extrapolate dictionary to define operators? Is it because of some novel effects like state dependence in quantum gravity, or we need or just the naive prescription of ADS CFT for some reason couldn't use the
So if you're just using the extrapolate dictionary, then you need some way to like causally connect the thing you're trying to reconstruct to the boundary. So naively, at least, that just gives you the causal wedge. I actually have a paper coming out with Netta Engelhardt and Arvin that's arguing that actually by sort of causal reconstruction using the extrapolate dictionary, you can actually get significantly more than the entanglement wedge, but you still can't get behind an extremal surface. So if your black hole has a quantum extremal surface in it, which we now know they very often do, then you, just by the quantum focusing conjecture, you can never causally get a causal connection between something behind that quantum extremal surface and the boundary of the spacetime, and so you can never use the extrapolate dictionary to reconstruct it. That's sort of the problem.
Yeah, the prescription of entanglement wedge reconstruction seems to tell us something about the interior of black hole, like the gauge office wall protocol or the EWR prescription, but I'm worried as to how much it can tell us about the interior and what are some hindrances to describe ultraviolet effects like similarity using this prescription.
So yeah, the hindrances are one, you've got to causally connect it. Like the only clear element of the dictionary we have is the extrapolate dictionary. So you've got to somehow at the end of the day connect the thing you're reconstructing to the boundary, have something get out to an asymptotic boundary. Like maybe with entanglement wedge reconstruction using PETS maps and stuff, you can have it be connecting to some Euclidean boundary and some Euclidean construction of the state or something like that. So that's one issue. The other issue is that normally to make the reconstruction work, you need to assume the bulk dynamics work in a certain way, right? If really what you're using is the extrapolate dictionary, then to use that to construct a dictionary for operators that aren't out near the boundary, you need to assume the bulk dynamics behave in a certain way. And so it can't really teach us new stuff about the bulk dynamics because we had to assume the bulk dynamics work in a certain way to have the reconstruction work. Right?
Yeah,